first speaker is Robert Kropholler from Warwick, who's going to tell us about Dehn functions of subgroups of hyperbolic groups.
Yeah. Thank you so much for, thanks for being here. Thanks to the organizers for inviting me. It's a real pleasure to be back. So, yeah, I'm going to be talking about Dehn functions of subgroups of hyperbolic groups. Try and tell you about some recent work with Claudio Eisenrich and Ignat Soroku. So first, I guess we all probably know this, but I'm going to just give the definition anyway, just to remind everyone. So if you're given some group G, which is given by some presentation, M, okay, and you're given some word W, which is equal to the identity in G, then the area of W is the minimal K such that W is a product of K conjugates of relations. Wi, Ri plus minus 1, Wi inverse. Okay. So in some sense it's, you're given a word that's trivial, that tells you that it's in the normal subgroup of the free group generated by the Ri, and you're looking for the minimal way that you can write it as a product of the obvious generating set for that normal subgroup. Okay, and the Dehn function, D sub G is a map from the natural numbers to the natural numbers, and so it takes in an n, and it maximizes this area, so it's the maximum over the area of W, such that the length of W is bounded by n. I guess very simply defined, W better be the identity. Okay, so I always say at this moment that it's some measure of complexity of the word problem, and if Saul was here, he would grumble and tell me that that's not true, so it's not really true, but in some sense it's giving you some upper bound on how hard it is to solve the word problem, right? If I can, if I sort of know how many products of conjugates of relators I'm going to need, if I give you a word of length 100, you can just write down all of those products of conjugates of relations, and that will let you check if your word is equal to the identity. Okay, so this is a very algebraic formulation, right? I want you to, in this talk, think of something more geometric, but I'm going to be very hazy with the definition. So I want you to think about, think of W as a loop in the Cayley graph of G, and so if I have a loop in the Cayley graph, right, that's what it means for W to be the identity, then if I attach two cells to every relation, I get a simply connected space, and so I can see that as some sort of cellular map from D2 to what is now going to be the Cayley complex, and you're counting the number of cells in this. Okay, so that's extremely hand-wavy. If you've never seen this before, this is completely useless, and if you have seen this before, you're probably bored at this moment. So why do I do these things? Okay, so this is the Dehn function. Okay, and it's it's a theorem. Oh, I guess I should say something. Right. Yeah. So sorry. So here, there's some geometric way to think about this in terms of disk diagrams, and I'm not telling you the full details, but you can sort of figure things out. And obviously, I've sort of said that this is an invariant of G, but it relies on the presentation. So there's some equivalence you want to put on these functions, which is, we say that if you're given two functions from the naturals to the naturals, f is less than g if there exists some constant c in naturals such that f of n is less than or equal to cg of cn plus c plus cn plus c. Right, so this is some ordering on functions, right, and f is equivalent to g. G and G less than F. Okay. Right, and so you can check, you've never seen this before and you get board, you can just go, like, pick a different presentation and prove that you get equivalent functions. It's not hard. It's a basic exercise. Okay, so this is well defined up to this notion of equivalence. Okay, and then the amazing result is that, so the first result that I think is kind of amazing is the theorem of Gromov, which says that if you have a finitely presented group G, so G finitely presented, it's hyperbolic if and only if the Dehn function of G is equivalent to a linear function. Okay, so linear functions completely characterize hyperbolicity. Okay, and from here, so what you can actually sort of remarkably prove, even more so, is that it's not just being linear, it's actually being sort of small enough, right? So if you, in fact, if the Dehn function of G is strictly smaller than quadratic, then G is hyperbolic. Okay. So this is what's known as the Gromov gap. There's a gap, you have linear things with hyperbolicity, and then suddenly you don't get anything between n and n squared. And then, because it's a theorem that I very much like, so it's the theorem of Brady and Bridson, that for exponents of things, you really do get everything else. So if you take this set of alpha such that n to the alpha is equivalent to the Dehn function of some g, right? This is some subset of the reals, then Brady and Bridson proved that the closure of this subset is, it contains one, that's hyperbolic groups, and it contains everything else. Okay, so this is really there's only this one gap. I'll come back later. Grab this while I see it. Okay. Right, so this is what we know, and if you asked sort of what we know about Dehn functions for all groups, I mean, a lot is known. And actually, so I sort of stated this result of Brady and Bridson. It's quite, of course, I mean, they give a dense set in here, but in fact, there are results of Berger, Olshansky, Ripson, Sapir that give sort of a much sort of closer characterization if things are bigger than 4. So you can really say a lot about what functions appear as the Dehn functions of finitely presented groups. Okay, but you could ask, or a question that I think is natural to ask is, you have your favorite class of groups, surely we all do, and you could ask, well, what Dehn functions appear, you could firstly ask what Dehn functions appear for your favorite class. If your favorite class is small, like hyperbolic groups, then I've answered that question. If your favorite class is something like cat zero groups, then you're only getting n squared. So maybe a better, broader question is, what Dehn functions appear for subgroups of your favorite class? And so a lot of study has been done in this for things like cat zero groups. Okay, so what about, let's write it like this. So let's say C is a class of groups. I'll just say it like this. So the isoparametric spectrum, maybe for C, is going to be something like the alpha, such that n to the alpha is a Dehn function for some h. H is going to be a subgroup of G, and G is going to be your class. Okay? So maybe your class is rigid, right? In a short moment, I'm going to start talking about hyperbolic groups, where it's not interesting to ask what are the Dehn functions of hyperbolic groups. Gromov tells us this, but it's maybe more interesting. Okay, and so for say the class of cat zero groups, so something like the class of cat zero groups, this has been really well studied, and so for instance, you can get fairly surprising things. So I think, n to the k is in IPC for all k in the natural numbers. Okay, so you can get arbitrarily high degree polynomials. If I'd sort of written this slightly better, I mean, you can get sort of exponential functions appearing as Dehn functions of subgroups with cat0 groups. You know, e to the n, this e to the n is equivalent for Dehn function h sub cat0 group. Right, and somehow there's lots of tricks you can do to sort of soup up weird things. Okay, you can ask the same question for linear groups. For linear groups, I think even more is known. So you can get all of these examples. In fact, the things I've written down here, you get inside special groups. But in linear groups, for instance, you can get sort of arbitrary towers of exponentials. Right? So you can get some really wild things happening in your favorite class. Okay, so my favorite class, at least for this moment of time, for the next 39 minutes, is hyperbolic groups. What about C equals hyperbolic groups? Okay, so I think 8 years ago I spoke in possibly what was NPC W01, and I think I was talking about some sort of similar things about subgroups of hyperbolic groups. The world has changed since then, but I'm going to tell maybe a story that I told then, which is, okay, so, let's look at the class of subgroups of hyperbolic groups. Right, so the first question is, what can you say? And you might, if you're very hopeful, and you haven't read that many papers, think that if you had a finitely presented subgroup of a hyperbolic group, it's hyperbolic, right? So maybe, if everything was perfect, maybe when you're looking at subgroups of hyperbolic groups, you don't get anything more than linear. That's sadly not true. Well, sad is a matter of perspective. I think if it was true, I wouldn't have got where I am. So it's the theorem of Brady from '99, which says that there exists a finitely presented subgroup of hyperbolic group that is not hyperbolic. Right, so the way you prove this for, it's another one of these things where if you know what I'm writing, then you probably know the story, and if you don't, then it's not helpful. But right, the way you prove this is you prove that it doesn't have a finite classifying space. You prove that actually any classifying space has to have infinite 3 skeletons. Okay, and in 1999, this was the only example of this type. And when I spoke here 8 years ago, there were some variations on this theme by myself and Yash Loder, and I was attempting to do some work with Federico Vigolo about sort of creating new hyperbolic groups where you could prove things like this. And we got some results in that direction. But this was basically all we had. We had one example and we had variations on this example.
What is the Dehn function?
Oh, comes up. So, yeah, we have variations on this example. But the difficulty is, so if you, the problem with hyperbolic, okay, so, sorry, just to say something like, one problem with hyperbolic groups is when you're constructing groups with sort of interesting finiteness properties, a really helpful thing to do is just take products. Turns out that that's a great way to construct groups with interesting finiteness properties. And this is really good if you're working in something like cat0 groups or linear groups. It's very bad if you're working in hyperbolic groups. So this problem really became, it's just a very hard problem, but in the last 8 years, an amazing amount of progress has been made. So I want to sort of say 2 results. So it's the theorem of Italiano, Martelli, and Migliorini from, well, I guess in my mind it's 21, but probably the published date is different. I can look out and find Giovanni, 23? Okay. Okay, so there exists subgroups. Let's say it like this. There exist non-hyperbolic subgroups of hyperbolic groups with finite classifying space. Finite. Okay. So Noel gave this finitely presented example, which wasn't at type F3. His methods were sort of, well, you know, they use branch coverings of some very particular complex, which was why generalizing is very hard. These use some sort of very clever Coxeter polytopes in dimension 5, and some Dehn filling arguments. Right, and even more recently than that, so it's the theorem of Claudio Eisenrich and Pierre P, that there exists non-hyperbolic subgroups of hyperbolic groups of type Fn, not Fn plus 1. Okay, so right, so you can sort of do this finiteness properties thing. You can actually do it in all dimensions, right? And these use complex hyperbolic lattices in complex hyperbolic space. Okay, so I mean, you know, as I say, eight years ago we knew this, and now we sort of have a much bigger wealth of examples. And so, so we now have a wealth of these examples. We have way more finitely presented subgroups of hyperbolic groups than we had back then. And so now, this gives you some possible way of, you know, coming to this question of, well, what does the class of Dehn functions look like? Right, and so here's a trivial observation. Right, so let's the Dehn function of n, the Dehn function of h, is at least quadratic for all these groups. Okay, so it's easy to get a sort of trivial lower bound. You can say n squared just because you know they're not hyperbolic. And very sadly, that's where the lower bounds end. Okay, this is really all we know, right? So, you know, for any of these groups, if you can come up with some method which gets you a better lower bound than this, even n to the 2 plus epsilon would be an amazing improvement. We really don't, you know, the techniques we have, we're really not able to get our hands on these lower bounds. So today I want to talk about upper bounds. Okay, so, right, so what I want to do, right, so for upper bounds, there was this old theorem of Gersten and Short, from I think the early 2000s, so very shortly after Noel's group, where they said, suppose you have a hyperbolic group G, and N is a normal subgroup of G, N is finitely presented, and the quotient is free. Okay, so suppose you're in this fairly particular situation where your group is co-free, it's a normal subgroup and the quotient is free, then they can actually prove that then there exists a K such that the Dehn function of N is bounded by. Okay, so if you're the kernel of a map to a free group, you're polynomially bounded. And actually some more recent work of deducing this was a good one. This looks good to me, but does it look good to... No. Okay, okay.
Is there an example of this?
Of this?
Yeah, just that.
Oh, yeah. Yeah, I promise I'll get there. So actually, more recently, okay, green actually seemed good. At least I could read it, so.
So is it free non-abelian?
Yeah, it's free, they prove free non-abelian. Let's not trip over that. Yeah, but Claudio, more recently, was able to say, well, if G mod n is free, you have Gersten and short, but Claudio said, same result, but free abelian. So if the question is either free or free abelian, then you have polynomially bounded Dehn function. Okay, and now, I told you we have this wealth of new subgroups of hyperbolic groups, but actually, if you look at all of them, so both of these examples are appearing as kernels of maps to Z, right? So both here, H is the kernel of some map G to Z. Okay, and the same is actually true here for in the original paper of Claudio and Pierre. Their groups are appearing as you take a complex Morse function, then you take the real part, so you're getting some real Morse function, and actually it's the kernel of some map to Z. In later work, they've managed to say that actually you can get kernels of maps to Z squared, and Claudio and I have constructed finitely presented groups that are kernels of maps to Z to the n. But right, I'm saying free abelian every time here. So actually every single subgroup of a hyperbolic group that is not hyperbolic fits this theorem. Right?
The green version?
Sorry? The green version. It's very close to fitting the original one with Z.
But why do you need to be free abelians? Is abelian is enough?
Abelian's enough. Yeah. Sorry, yeah. You can, finite. You can always pass to finite index in this story. So.
Can you say something about K?
That's probably what I'm. Yeah, that's going to be the rest of the talk. Okay. Sorry, I'm moving too slowly or in the wrong order. So I just wanted to point this out as, so as I say, I think 8 years ago, I was here and I was like, please come up with new ways of constructing non-hyperbolic subgroups, and that worked. Okay, so maybe if I say this today in 8 years, come up with new ways of constructing finitely presented non-hyperbolic subgroups. Okay, and we really need some new technique. I mean, the problem is that the only real techniques we have are Morse theory. Okay, I'm sure that there are other techniques, but if you have one for constructing finitely presented subgroups, please find me and we'll see if we can come up with some hyperbolic groups. Right? So, so for all groups, for all subgroups we know, subgroups of hyperbolic groups, know the Dehn function is polynomially bounded. Bounded, and so in fact the question that I really want, the question that I'd really like somebody to be able to say something about is, does there exist H subgroup of G, G is hyperbolic, the Dehn function of H is exponential. Right? Can you find some subgroup with exponential Dehn function? Right? And as I say, the problem is that the methods we have right now, they're just not going to get you anywhere with this problem. You really have to come up with some completely new way of getting your hands on this subgroup. Right? It can't appear as the kernel of a map to Z to the n or some free group for that matter. Right, and actually, sorry, just to say, I mean, I think in some sense, yeah, everything we know actually appears as a map to a free abelian group. We don't actually have any examples that appear as the map to a non-abelian free group. So even doing something like that would actually be something very nice. Okay, so Claudia and I knew this, and I think every time we meet, so Claudia's been an extremely good co-author. We've managed to prove quite a lot of things, but every time we meet, we spend the first 2 days discussing questions like this. Questions like, what are subgroups of hyperbolic groups? and we make very little progress. But we managed to say something. So in the case of this, so theorem, this is me, Claudio, and Ignat. We managed to show that for Brady's group, we give it a name n, the Dehn function of n is bounded above by n to 96. Okay. Right. And so for this group, and actually variations on this group, we were able to give an upper bound. And okay, maybe I want to sort of tell you how that story goes, and what one could try and do, and what we actually did, and then sort of say some words about how you might apply this to these. But the point is that, so this upper bound would be way better if it was 3. It would also be way better if we had a lower bound, which was like 90. But we can't do either of those things. I mean, in terms of, and just to say, so in terms of what I think is the truth, I think that for at least Null's group, the Dehn function will actually be n squared. Somehow it's the easiest way to construct such a thing, and it would be very surprising to me if you could make it really go on to infinity. Also, it's a branch cover of a Beery-Starling's group, so and those have quadratic Dehn function, and so somehow you should be able to lift that. Depending on the day you talk to my co-authors, they'll tell you differently and tell you that they think that Null's group has a lower bound of n cubed. And so the answer is we really don't know. Okay. Any questions about anything at this moment?
Can you tell us how to constructing a subgroup K0 group with exponential Dehn function?
Oh yeah, I can. So I think it's not. Well, one way to do it is take a guy like this that's hyperbolic, and so you take something like this that's hyperbolic, and Hagen and Wise show that it's cubulated, and so then sort of all of the work of Agol and Wise, you get that it's virtually special. So this group embeds in a rag, and then it's actually not so hard to embed the double in a slightly bigger rag. And then once you've done that, you can see that the Dehn function is, the Dehn function of the double relates to the distortion of this subgroup. And if this is hyperbolic, then that's, right, and actually that's, so that's also how you get these. You take different, this is, sorry, so some of this is work of Brady and Sorokin. Okay. Right. So I wanted to, okay. So what I decided that I wanted to do is I wanted to give you sort of a sketch of how one would prove this theorem. And through that sketch, you'll see at various points the things that you need to know to sort of run this machine on this group. And then I'll tell you why we just couldn't do that, because life is too hard and we actually had to just reprove this theorem in a different way. But I think the proof is very nice. Okay, so proof of Gersten short. It's the proof of Gersten short intersect Claudio, so the proof when G mod n is set. It's not. Okay. I'm slightly sleepy after lunch, so we're going to do an easy thing. Okay, so I have this hyperbolic group G, I have this normal subgroup N, I have this quotient which is isomorphic to Z. And so the first thing that you do, the first ingredient you're going to need is So n has some finite presentation. x1, xl, r1, r. Okay? And because this is z, so this is a place where things get slightly easier, you know, this gives you a split short exact sequence, and so G is n semi-direct Z, right? So this is what Gersten and Short originally did for the free group. So you can write down a presentation for G. Rm and T xi T inverse is phi xi. Okay. Okay, so you write down a presentation for G. And now, let's draw this picture bigger. So now I take some word in the letters of H which happens to be trivial. So W is some word. So let me say like this. So W is some element of the free group on the X's. XL. W is 1 in N. So we have this loop, W sitting inside the Cayley graph of N with respect to this generating set. Okay, well, this is sitting inside G, so W is also equal to 1 in G. It's also equal to 1 in G. So now I have this loop inside the Cayley graph of G, right, realizing that you know, with these two generating sets, the Cayley graph of N is a subgraph of the Cayley graph of G. So I can build this disk diagram in G, right? And so I'm going to fill this loop in G. G, right? Algebraically, I'm saying this W is a product of conjugates of these relations, and I can do that, and I can do that in a way that I understand what's happening, right? So the area of W is less than or equal to C times the length of W. I don't want to use C. Okay. Okay, well, if you've never used any of these relations, then you're done, and you've got a filling for your word over the subgroup N. So that would be great, but probably that's not going to happen. Well, if that always happened, you would have proved that N has linear Dehn function. So somewhere in your diagram, there's an edge labeled by T, right? And now here comes just the trick when you're working with things like H and N extensions, right? Well, the only relations that use T, I mean, T isn't appearing anywhere in here, it's only appearing here, and here it appears with an inverse, right? And so I'm going to have some relation that looks like this, right? And then I can keep doing this, right? And eventually, you know, fairly obviously, this is going to loop round, and I'm going to have what's known as a T ring. Okay, so I have a ring of these T relations, and they sort of cut this diagram up, and they might do things like maybe I have one, maybe there's another one inside. Okay, so I get a bunch of these T rings. Okay, and so now I'm going to look at one of these. Okay, a bunch of T rings. So look at an innermost T ring. Right? Let's look at this guy in the middle here. Right? And suppose that inside in this sort of inner region, right, this is still a loop. The boundary label is labeled just by x's. Right? So it's still a word in N, it's still the trivial element because it's a loop. So this inner word, so inside here there's some diagram. Inside this small circle, there's some diagram for this outer word just using these relations R1 through Rn. So look at an innermost T ring. Okay. And okay, let's just suppose for this moment of simplicity that actually this inside diagram is really simple. I just read one of my relations around the boundary, right? So the inside loop is just labeled by a relation, right? And so the outside loop, right? So the outside loop has label phi of Ri, right? Okay, so I'm making a choice here, right? So it could either be phi of Ri or phi inverse, right? And I'm just picking it so that it's phi because it's going to make my life easier. I'll tell you where the lie is, but let's just suppose for a second that all these t edges point in. So this is some relation. When I conjugate, there's an x here. I'm just replacing it with phi of x on the outside. So there's label phi of Ri. Okay, well, the label phi of Ri, so the length of this label is length of phi of Ri is less than or equal to, say, alpha times beta. Alpha equals the maximum of the length of the Ri's, and beta is the maximum of the length of the phi of the xj's. Right, you replace each letter in Ri with whatever its image is. Okay, so you can compute the length, so it's less than this. And so, what I can do is, I have this small diagram, I have this, this inside thing, I can cut this diagram out, and I can put a diagram for phi of Ri, right, it's still the trivial word, it still gives you the trivial element. I can put a diagram in of some area which is just, which sort of just depends on this constant here, right? So, let me write something down, maybe a little bit less vague. So, what I'm trying to say is that there exists a filling for phi of Ri with area less than or equal to the Dehn function of n applied to this constant alpha. Okay? So I can replace, so if I see an innermost T ring, okay, so I did this for a single relation, but if you do this carefully, I mean, you know, it's not Thursday afternoon, you can figure out how to do this for some sort of diagram and you get the same thing. So in fact, I'm going to give this, I'm going to call it C. Right, so you can do this across the whole diagram. So you can cut out an innermost T ring, you can remove it, and glue back in something. And what you've ended up doing is you've taken whatever area was inside and you've multiplied it by this constant C. Okay? And you could do that simultaneously to all innermost T rings, and then you just repeat. Right? And once I keep doing this, eventually I'm going to get rid of all of the T rings, and so I've got rid of all of the T edges, so I have some diagram over H. And so if you think about, well, how many times do I need to do this process? So each time I do this process, I multiply the area by C. Okay? It's going up by a factor of C. How many times do I have to do this process? Well, the worst thing that could happen is I have a nested, I have a giant stack of nested T rings, and I really have to sort of like deal with the innermost one and then deal with the next one. And so the most you have to deal with is actually, if you think about it carefully, it's the distance from any vertex of your diagram to the boundary. Right? The worst that happens is a very big stack, and how far do you have to go in that very big stack? Well, it's what I'm going to call the radius of your diagram. And so what you end up with is the Dehn function of n is bounded by, say, the area, which I already put down over there, some constant b, I'm not going into, but it just depends on g, times c to the, okay. You think you can do better when you're at the board, and I never can. Okay, let's say it like this. So it's the area of this diagram times c to the power of the radius of this diagram. Okay? Each time I apply this innermost T-rings argument, I multiply the area by perhaps c, and I have to do that at most the radius number of times. Okay, so if I knew these two functions, I'd be happily done. And that's, so Gersten and Short exactly deal with that. They tell us that for G hyperbolic, there exists a diagram for W with area less than or equal to the length of W and radius less than or equal to delta, right? I guess I should say delta hyperbolic. Delta log the length of W. Okay. And so if you put all this together, right, if you're quick with these things, right, you can sub in here, oh, sorry, no, I told a lie again. The length of W times log the length of W. Okay? So in a hyperbolic group, you know that there's a diagram with area linear, with linear area. But Gersten and Short say, well, let's make the area slightly worse, but if we do that, we can get a good control on the radius. Okay, so these two things are playing off against each other. And so now if you put this back in here, right, this is telling you that the Dehn function of n, I used delta too many times. Okay, everyone's hopefully. Dehn function of n bounded by n log n c to the delta log n, right? Which is some polynomial in n, right? And so there are basically three things that you really needed to know in this proof. Maybe four. Okay, the first thing you need to know is you really need to know a presentation for n and g. That's actually where we're shot. I mean, that's a bad time. The next thing that's obvious that's going to be a very bad time is you need to figure out this constant. Okay, this is, right, if you want to know what this polynomial bound is, you're going to have to figure out this c. And the last thing you're going to have to know is you're going to have to know the delta hyperbolicity constant for g. Okay, if we just go back to step one. So step one is get a presentation for g, or get a presentation for n and use that to get a presentation for g. We don't know how to do that. Right, so a sort of back of the envelope calculation suggests that if you do this for Knoll's group, which I think is one of the simplest groups to write down as a subgroup of a hyperbolic group, this thing has about 6,000 generators and about 8,000 relations. So I stand no chance of being able to sort of deal with this process. And actually, I mean, then I have to understand some automorphism of that group. I want to pick like a good representative. I mean, you know, if you're very good with computational algebra, maybe. So if you're very good with computational algebra, I think it would actually be interesting to get a presentation and try and see if you can run this machine and see if you can get some better bounds. We're not. Yeah. So first we thought, well, so we read Gersten and Short carefully. We understood the proof. We understood that all hope was lost because we were never going to get a presentation that we could work with. And then I think we went back to thinking about Dehn functions of subgroups of products and didn't revisit this for a while. We then started talking to Ignat and we all realized, so we had sort of similar thoughts about trying to do this. And we realized that, well, doing this algebraically is just not the way to do it. So Knoll doesn't give you, you know, as I say, writing down a presentation of G is really hard. So Knoll's obviously not giving you a group. He's not saying, here's a group, it's hyperbolic. He's not writing it as a semi-direct product with Z. So what's he doing? He's getting it to act on a cube complex, right? And so what we do is we look at, for Brady's group, G acts on some cube complex. Okay, and he proves that it's hyperbolic by proving that this cube complex admits no isometric embedding of a flat plane. And so we were actually able to upgrade that. So we were able to say that theorem that Q complex X, X is 5 hyperbolic. Okay? So the first thing we did was we managed to say, okay, well actually you don't have to care about the hyperbolicity constant for G. You can do this all geometrically. Don't do this algebraically, do this with the cube complex. And for the cube complex, we can get a very small bound on the hyperbolicity constant. We can prove that it's 5. Okay, this uses work of Boy and some other people about hyperbolicity of median algebras. Okay, and so you're looking for embedded squares, and we just have to sort of figure out what the largest embedded square is. Right? So that was one step out of the way, which was pretty good. We didn't need to get presentations. Instead, we had that null subgroup n is acting on some level set of some function from x to the reals, and this was sort of taking the place. So this cube complex and this level set were taking the place of our two presentations. We're able to compute the hyperbolicity constant, and then the last thing on this list of things to do is to compute this expansion constant. And so we managed to sort of give an idea of what this expansion constant should be geometrically, right? So C is the expansion. Well, C measures, say it like this. C measures what happens as you pass over critical points or vertices. Okay, so when you have this filling, sort of the idea is that by cutting these T rings out and gluing something in, you're sort of pushing things down. When you try and do this geometrically, you can sort of push things until you hit a vertex, and then you have to understand what happens as you pass over this vertex. And as you pass over this vertex, I mean, it really sort of depends on the ascending and descending lengths of this Morse function. But the point is that for Knowles group, those are really understood. They're just suspensions of cycles of length 20, right? So you really get a grasp on them, and in fact, I think we were able to show that C is less than or equal to 20. Okay, and so if you put all of this together, minus perhaps I've told you some small lies, you get the 96. Okay, and so we actually managed to. So this theorem, I mean, what I should say is that this theorem here actually applies to all of the generalizations of Knowles groups by Yash and myself, so it also applies to the Lotus group. And so actually, sort of this seems to me, like the first step you could try and do in understanding these things would be understanding the hyperbolicity constants, right, and seeing what you can get from that. Yeah, okay, so I think I'm going to stop there. Thank you so much for listening.
Regarding that theorem, the upper left,
Yeah.
have you guys thought about if it's possible to do something similar with generalized Desvigny-Brady groups?
Oh, you mean just like so people have done this with Desvigny-Brady groups inside RAGs, and you get that they're always bounded by n to the 4. And so the argument, depending on how you look at it, it's a similar sort of thing to this version. And so you can do it in other contexts as well, but we haven't. Yeah, but that's all I know off the top of my head. Maybe we can talk.
Yeah, I think you're asking a question, but in this extension to the Gerson-Schurz theorem, do you know what happens if you look at quotient being a RAG in general?
Yeah, so we definitely don't know. I mean, So Claudio was, so the way that this theorem came up for Claudio is he was asked to translate Wren's thesis, which talks about the second sigma invariant. And I think while he was translating it, he realized that actually there was more that could be done, and in showing that it's finitely presented, I mean, the second sigma invariant controls finite presentability of kernels of maps to Z. And in sort of going through why it's finitely presented, you could actually get some bound on the Dehn function. But so for kernels of maps to rags, we just don't have any good, we don't have any good model of like, how do you understand the kernel?
Is there an intuitive idea of why allowing a larger area in your diagram gives you better control of the radius?
I'm not sure I immediately have a it's not obvious to me I have a sort of good answer for that. But you could definitely I don't have a good answer for that. It just sort of comes out in the proof when I guess really what they wanted to control was they really wanted to get some diagram where they could control this better than just the area. So sort of the radius is always sort of comparable, is always bounded above by the area up to some constants. And so I think they really just wanted to make this better, and this is just what pulls out.
So how close is this 96 to optimal, do you?
I think 2 is optimal.
It is optimal.
So I think n squared. I think n squared is probably the correct answer. So, as I say, I think the thing we don't know, we don't really know how to prove better upper bounds. That's one thing I will say. And we have ideas of proving lower bounds. We have some ideas that we occasionally talk about, but we've never managed to make any of them work. So, as I said, just because, for me, I think that Brady's group is a branched cover of a Beery-Starling's group, which really does have quadratic Dehn function. And somehow by passing to this branch cover, one might hope that you could prove the Dehn function doesn't get that much worse. And so I think quadratic is probably what one should expect in this case. I think you would have to do something more exotic to get some genuine.
If I can ask another question. So if you wanted to write 96 in terms of geometric, with a geometric meaning, you would use the hyperbolicity constant here and the constant C? Or?
Yeah, if you put them, exactly. If you just put all those, this bound is, so they prove it for hyperbolic groups in the Cayley graph, but we reprove it for hyperbolic cube complexes. And so you just stick everything in here and put it in here. You should probably get 96. I might have messed something up slightly. Actually, like, the reason that, somehow 96 might not be optimal. It might be very easy to see, actually. We might have even done something like it's 95 times log n, and so then we were just like 96.
Does this group have a chance of being cut zero, or?
Well, so this group can't be cat zero because it's not of type F3. But something like the Italiano Martelli Migliorini group could be cat zero. Okay, there's a shrug. So, but because it's of type F, there's no reason why it couldn't be. We really just don't know.
More questions? Just a small one. So, do you expect that if you fix your group, there should be like a uniform up or down for all possible?
No, I don't see why. It's not obvious to me that would be true.